Okay, now that we've gone through a fair amount of the rotation information, I thought it'd be useful to return to one of the more complex examples of how we use rotation in combination with just linear kinematics as well. So I want to talk through an Atwood machine, and to date we have assumed that when we look at Atwood machines that we're not going to worry about the mass of the pulley, but it does have an effect, especially if you have a larger pulley. So I'm going to walk you through is the how to analyze an Atwood machine where the pulley does matter, and how to connect rotation. And that's the plan for the next few minutes. So so here we are. We're going to make an Atwood machine. So it's going to be a full Atwood machine. So there's going to be a pulley, which in the past we have ignored. There's going to be some mass here. I'll call this M1. There's going to be some other mass. I'll make this larger, and this will be M2. In the past, what we've been able to do is we've been able to look at the forces acting on M1, the forces acting on M2, or the forces acting on the whole system. And we can sum the forces for my whole system. And if I set the direction of motion, the sum of the forces are going to be those in the direction, M2G, positive, and subtract those forces going against the direction of motion. And we'll set this equal to our total mass times acceleration. Right? So we can't do this if the pulley has some mass. And so what we'll do is we'll check this, right? So this is the way that we would tackle an Atwood machine if we have a negligible mass pulley. But when the pulley has mass, so some of that force of gravity that's accelerating this M2, some of that is dragging along M1, but some of the force gets consumed by getting the pulley to rotate. So we're going to have to take that into account. And let me show you how we do that. So let's set up a common scenario. So I'm going to have a disk here. I'm going to say that the moment of inertia for this is going to be that of a disk. So I'll look that up. So a pulley can be considered as a disk, but you can't assume that. So it's going to be 1/2 times the mass of the disk times the square of the radius. So notice I have 3 masses, right? So I have some radius in my disk. I have a hanging mass 1 and a hanging mass 2, and then I have a mass of a disk. So I'm going to have to keep all of these straight. So we have a moment of inertia. Let's give some numbers to this. So let's say it's 15 centimeters in radius, and let's give it some significant mass. So the mass of the disk is going to be 0.80 kilograms. We'll have the hanging mass be 0.20 kilograms. And the driver mass, let's not make it very big, so let's just make it 1/2 kilogram, so 500 grams, and see what we get. So the way that you want to start these sorts of diagrams is all the same, right? So I'm going to draw some diagrams, and I'm going to diagram what are the forces acting on M1 and the forces acting on M2. The thing I'm going to add into this now, in addition to those force diagrams, I want to draw a torque diagram to represent what's happening to this disk. Right? So here are my 3 diagrams. All right, so let's do this over here. So I'm going to have the forces acting on M1. Right? Well, what do I have? I'm going to have M1G pulling down, and I'm going to have some tension here pulling up. I can sum those forces acting on that. So it's still the same as we were doing before, right? My direction of motion is this way, so this is going to be positive for this diagram. So I'm going to have my tension minus M1G. And this is going to be equal to this mass times the acceleration, right? So this is all still true. I'm going to have a second diagram, so I want to look at my second mass. Right. Notice now my direction of motion is different, so I'm going to make this positive. So I'm going to have M2 times G, and I'm going to have tension here. Here's the tricky part, right? So when this pulley is negligible, these 2 tensions are the same, but that is no longer true. So now some of that force is being transmitted along this wire. Some of that force is going to be consumed in getting this to rotate. So we're going to apply a torque, and not all that force is getting transmitted to M1. So I'm going to have the tension here, I'll call this T1, and I'm going to have a tension here, which I'll call it T2. It's really important to recognize that the tension now is different amongst these two. and some of that force is being consumed by rotating this disk. So this is the sum of the forces acting at 1, the sum of the forces acting at 2 now. Well, I have m2g, which is now positive, minus t2, and that's going to be equal to m2 times acceleration. Notice it's the same acceleration, right? So that's still handy. They're all physically connected, so they'll accelerate at the same rate. So the third thing I need, though, is, and if this was a negligible pulley, I would stop here and I'd combine these together. My tension would be the same, and I could figure out whatever was asked of me. But now I have a pulley, so what I need to do is make a torque diagram. So a torque diagram is not a force diagram. Right? So here's my torque diagram. So I'm going to have this tension T2 pulling in this direction, right? This is going to get it to rotate. But notice I have a tension. This is in the direction of the line, right? So the T1 is pulling in the opposite direction. I have radius on either side of these. So I have two torques that are acting on this, right? So I have 2 points of contact. So I can sum my torques. Just as I sum my forces, I can sum my torques. And some of my torques is going to be, let's see, so I want to think about this. So this is my direction of rotation. I've said that's positive, right? So traditionally we make counterclockwise being positive, but I have to be consistent with my sign between my forces and my torques. So I'm going to make clockwise positive in this case because it makes sense. That's how I set it up. I have to be consistent. So the sum of my torques now, right? So I'm going to have this torque, which is tension 2, which is a force times R. Right? So that's a torque in the positive direction. And now I have this force that's going in the opposite direction, also times R. Right? So my force is, my torque is my force times lever arm. The lever arm is the same. So this is going to be not equal to MA, but now to I alpha. Right? So this is going to be equal to a moment of inertia times angular acceleration. Well, I've got 1, 2, 3, 4 unknowns. So I need a connector to get down. If I had 3 unknowns, I've got 3 equations, I can make this work. So the connector between torques and between rotation and linear is going to be acceleration. So remember my 3 connectors were my okay, so the connector that I'm going to use between the forces and the torques is going to be the connector that connects angular acceleration to linear acceleration. So I can replace angular acceleration with A over R, and then I have 3 equations and 3 unknowns, right? I don't know tension 1, I don't know tension 2, and I don't know acceleration, and those are the only things that show up. So the math isn't quite as bad as you might think, but let me go through it relatively quickly so you can see where we're going. So what I'm going to do is I'm going to focus on this equation. I'm going to substitute in A over R. I'm going to rearrange these two for tension 1 and tension 2, and then substitute everything into this equation to make sense out of it. So I'm going to set up, I'm going to rearrange this one, so tension 1 is going to be M1A plus M1G. I'll rearrange this one, so tension 2 from that equation, and I'm going to move this to the other side, so it's going to be M2G minus M2A. And then I'm going to take this equation, which is T2 times R minus T1 times R. And this is going to be equal to the moment of inertia, which we've decided is a disk, 1/2 mass of disk times R squared. And I'm going to substitute A over R for alpha, so my angular acceleration. So you may notice that I can divide both sides by R, so then make this R squared, and these R's go away, and then this R squared will cancel. So the radius doesn't matter. The shape of it matters, but the radius isn't going to matter. So the thing that is going to matter is the mass, though. So the mass is going to affect this. So let me plug in and see where we get to. So I'm going to plug in for T2. T2 is M2G minus M2A. I'm going to plug in for T1, which is M1A plus M1G. And this is going to be equal to, what am I left with? I'm left with the mass of the disk times acceleration divided by 2. So now I have acceleration that shows up here, here, and here. And I need to just segregate this. So now I'm just doing recreational algebra. So let's see where we get to. So M2G, move all the A's to the other side. So minus M1G. This is going to be equal to M2A, which is positive on the other side, plus M1A plus mass of the disk divided by 2 times A. So what am I left with? So I'm left with M2 minus M1 times G. This is going to be equal to acceleration times M1 plus M2 plus the mass of the disk divided by 2. So this should look very familiar, a little bit familiar, right? So if I'm looking at an Atwood machine, I can get to the acceleration by taking take this. So without a disk, I would end up with an equation that looked like this without this mass of half of the mass of the disk. Right? So it's going to have an effect on acceleration, so that's good. Things can be going in the right direction. Yeah, so I don't know. I'm going to end up with acceleration. It's equal to M2 minus M1, so the difference of the masses times gravity, which makes sense. That's the driver for it. And then it's got to drag all this mass along, so this makes sense. M1 plus M2 plus the mass of the disk over 2. And now I'm going to plug in some numbers. So it was M2 ahead 0.5, M1 is 0.2. I'll use 9.8 because I'm going to use a calculator. And I'm going to add up 0.2 plus 0.5 plus 0.8 divided by 2, 0.4. So I get my calculator out, see what we get. So you have 0.3 times 9.8 divided by 0.7 plus 0.4 is 1.1. I get, what is it, 2.7? 0.67 is called meters per second squared. Okay. So this is the linear acceleration. If I want to get to the angular acceleration, well, I just divide by the radius, and then I'm there. So let's do a check. Let's make sure, let's see what the answer would be if we only looked at the forces, right? So if I only looked at the forces and I forgot about this, this pulley, or if they told me the pulley had negligible mass, let's see what the difference would be. So in that case, right, I can use the sum of the forces for my whole system, which is going to be it's going to be the two forces of gravity acting on it. So I'm going to have M2G in the positive direction, M1G in the negative direction. This is going to be equal to my total mass times acceleration. Or my acceleration now is going to be M2 minus M1 times G divided by M2 plus M1. Right. So no, it's very similar, right? So very similar equation, a lot easier to get to. Very similar equation, but doesn't have the mass of the disk in there. So I'm expecting I'm going to get a different answer. So I'm going to have, again, 0.5 minus 0.2 times 9.8. I'm going to divide this by 0.2 plus 0.5 only. So what am I going to get? I'm going to get 0.3 times 9.8 divided by 0.7. I get 4.2 meters per second squared. Right. So the pulley, again, I made it a massive pulley just to make sure there's a good difference there. Right? But the pulley does make a difference and does affect the speed of this. Again, the key things are that I'm going to make an individual diagram. So I have two forces and one torque diagram. I'm going to use Newton's second law 3 times, right? 2 laws with linear forces and Newton's second law of rotation. And then I'm going to use a connector to get those together, and then it just becomes algebra, and you get an answer. Anyway, hope that's helpful. I'll talk to you soon. Bye.